Hello everyone. In the previous discussion, we have understood about synthons and synthetic equivalent and then how we could start designing a synthesis or how we could have a strategy to build a disconnection approach and then we can do a forward reaction. In the present discussion, we will be looking into details of the synthons and synthetic equivalents. Synthons, as we have seen, they are formed due to heterolytic cleavage. Now, when we see heterolytic cleavage, that means we have to say that either one will be positively charged, the other one will be negatively charged. As well, we have said that synthons are the species which will be having some kind of charges associated with them. In this synthons, we can say that these are formed due to heterolytic cleavage. Synthons can be of two types. One is a donor synthon, the other one is called as acceptor synthon. When I say a donor synthon, it is supposedly formed because of the presence of the carbanion species, and when we say acceptor synthons, it can be said to be a carbocation species. When we say carbanion species, that means carbon will carry a negative charge. Carbocation species, carbon will carry a positive charge. Now for example, if it is an ethyl donor, that is C2H5 minus, the synthon comes from C2H5Li. That means it is associated with a electropositive element like lithium to give me C2H5 minus. That means now the carbanion has been formed. Further, if there is a presence of C2H5 plus, it is an ethyl acceptor. There, the synthon comes from a leaving group like iodide system, which will take the lone pair of electrons, leaving behind a carbocation. So, synthons can be said to be of two categories. One is said to be a donor synthon, which falls into the category of carbanion. The other one can be said to be an acceptor synthon, which falls into the category of carbocation. The formation of any CC bond involves the union of an electrophilic acceptor synthons and a nucleophilic donor synthon. Obviously, when I say that there is any CC bond formation, one should be an electrophilic in nature, the other section should be nucleophilic in nature. Here we can say that one part of the synthon should be electrophilic acceptor, like for example, ethyl acceptor. The other part should be a ethyl donor system like a nucleophilic donor synthon. Now, how does the disconnection take place? The disconnection of the bond is possible in three ways. One is homolytic cleavage, second one is heterolytic cleavage, third one is said to be concerted transformation. We need to now look into the details of this. When we say homolytic cleavage, that means there is a formation of a free radical species. That means equally the bond is cleaved and we get a free radicals. Such type of cleavage, they are called as homolytic cleavage. When there is a formation of ion system, that is the lone pair of electrons completely is shifting towards one carbon system, forming one carbocation and the other one carbanion, such type of cleavage is called as heterocyclic cleavage or heterolytic cleavage. It is said to be heterolytic cleavage. When we say concerted transformation, the formation of neutral species. Now this you must have seen when you have done a Diels-Alder reaction. When a diene reacts with a dienophile, it is going to give me a Diels-Alder adduct. When I try to do a cleavage of a Diels-Alder adduct like cyclohexenone system, and there is a concerted cleavage of the whole system, we can see here that simultaneously all the bonds are getting opened. In such a system, they are said to be formation of a neutral species. Now, for example, this diene is also a neutral species and the dienophile is also a neutral species. Such type of cleavages, they are called as concerted transformation. So basically we can observe that there are three types of cleavages. One is homolytic cleavage, the other one is heterolytic cleavage, and third is concerted transformation. If I see homolytic cleavage, I should be able to get free radical species. Heterolytic, then we will be getting formation of ions, and concerted transformation, they are going to give me neutral species. After understanding the type of synthons, that is whether they are donor synthon or acceptor synthon, we need to know what are their respective synthetic equivalents and from which type of reagent they can be derived. For example, R minus. Now this can be alkyl or aryl anion. They can be derived from RMgX, RLi, R2CuLi, that is dialkyl copper lithium. They can come from Grignard reagent, they can come from alkyl lithium. Their respective synthetic equivalent can be Rx. That means when there is a system like a synthetic equivalent, finally I want to get something which is present in the bottle, and hence their derived reagent can come from Grignard reagent or alkyl lithium or the dialkyl copper lithium. Their synthetic equivalent can be R minus, where this X acts as giving away the lone pair of electrons towards alkyl system and giving me a generation of carbanion. The second type of synthon is a cyanide. Here the derived reagent is said to come from NaCN. The synthetic equivalent can be HCN. The derived reagent can be sodium cyanide and the synthetic equivalent can be hydrogen cyanide. The next example is acetylide, where the synthetic equivalent can be an acetylene species and their derived reagent can be a Grignard reagent which is present on an acetylenic species, or a alkylated or an acylated system where there is a presence of lithium. Instead of acetylenic, lithium systems can be present. That can act as a derived reagent. When I come to a negatively charged carbonyl carbon system, it can tell to me that there is a presence of a lone pair of electrons on oxygen. That means if the electrons start moving towards the oxygen, then there can be a formation of double bond over here. In turn, when this double bond completely isolates itself, then there can be a negative charge once the electrons travel back to the carbonyl carbon. Now, such type of synthons can be seen if I can get an O with a metal system. That means this M system is associated either with a metal or boron dialkyl system. Their synthetic equivalent can be a carbonyl carbon with a long chain system present, or it can be a presence of methyl system. When I look at an ylide as a synthon, here ylide is nothing but triphenyl phosphine, where phosphorus is carrying a positive charge and carbon is carrying a negative charge. This can be derived from an intermediate where carbon will be attached to this proton, and in turn the whole intermediate is having an X minus as its outside anion system, or its anion which is going to balance this cationic species on the phosphorus system. Their synthetic equivalent can be something where it is HCH2X. In turn, I can get it with a phosphonium ylide system. Now when I observe, there is a presence of a long chain system, but there is a presence of the negative charge along with an electron withdrawing system like nitro group. We already know that the carbanion systems can be completely stabilized because of the presence of electron withdrawing system. In turn, their synthetic equivalent can be a long chain system containing a nitro group. In turn, the carbanion can be completely stabilized. So in such a way we can get some of this synthetic equivalents. The synthetic equivalents we just now saw were all donor type of synthetic equivalents. Now, there can be acceptor type of synthetic equivalents also. Now, for example, if the synthon is R+, it can come from RCl, RBr, RI, ROMS and R tosyl system, mesytyl system or tosyl system. RMOMS is mesytyl system and ROTS is said to be tosyl system. Only when this R is an alkyl system, I can be able to get an R+. Now, if I have got an synthetic in synthon where the carbon is going to carry a positively charged species or a positively charged system, I can get it when I have got a carbonyl carbon, because in the presence of carbonyl carbon system, oxygen will carry a negative charge and carbon is going to carry a positive charge species. If at an alpha position there is a presence of an OH and at a position there is a presence of a carbocation, that means there is a presence of a C+, it can come from an epoxide. Ring opening reaction of an epoxide system can give rise to a synthon like ROH+, or instead of that epoxide system, if I attach a Br system to it, then it can give me a synthetic equivalent where I can get a positive charge on the carbon adjacent to the OH. In this way, the next type of synthon would be, there is a presence of a carbonyl carbon CH2+. It can be generated if I just introduce a double bond across the carbocation species, where the whole double bond can be isolated so that one of the system will carry a positive charge, the other system is going to carry a negative charge. Now, for example, if this is completely moving, now if I look at this double bond system over here, we can see that there is a complete movement of the negative charge at one side and I will be able to get a positive charge at the other one. Hence, the synthetic equivalent is an ethene type of species containing C double bond C. If again I have to get a carbonyl carbon where on the carbon system I have to get a positive charge like this, I can do it with an ester attached to it. The synthetic equivalents can be an ester, they can be an acid chloride, or they can be an anhydride system. So dependent on which type of synthons we want to get or how we want to transform the synthons, I can get the respective synthetic equivalents. Synthetic equivalents are the real compounds through which we are going to do the real reactions, whereas synthons are said to be some imaginary system where we have broken down the bond so that we get an idea of what may be our starting material. Based on the synthon species, we can now calculate as to what are my synthetic equivalents. Looking at the synthons, I can imagine what may be the synthetic equivalents, and based on the synthetic equivalent, I can design my complete reaction. Now, for example, if there is a negatively charged species, as we have just seen, it can come from a Grignard reagent, it can come from RLI, it can come from dialkyl copper lithium or other any type of organometallic reagents. If there is a negatively charged system adjacent to a carbonyl carbon, it can come from an ester type of species. But one thing we have to see that if there is a very long system like CH2 present, we have to make sure that we do not lose any type of CH2 system, and then I generate a synthetic equivalent. So this is how we can understand about a donor synthon system and an acceptor synthon system. Further, after understanding what is the donor synthon and an acceptor synthon, I can finally arrive to my synthetic equivalent. After understanding the synthons and synthetic equivalents, now we need to understand about the disconnection. A common example in which previously we have discussed is orthoaminobenzoic acid. This compound is said to be orthoaminobenzoic acid. Now let us try to cleave this particular compound. At position A, if I am cleaving, I am going to cleave at C single bond N. and then there is a negatively charged species on benzene. If I try to cleave at position number B, I will be cleaving again on benzene, that is benzene is going to carry a negative charge and the carbonyl carbon is going to carry a positive charge. What we need to examine in all these possible disconnection, we need to see what are the different types of disconnection I can make. And then with more practice and an understanding of organic chemistry, I can now understand that how I can design this particular synthesis. But I just cannot decide on just one step backward, but I should have a more type of further aback system. That means just one step we cannot decide. Instead, I have to decide so that a complete target molecule can be brought. So it is always said that we must also remember not to look at backwards just one step, but to go further back. This is because most of the times just in one step if I imagine, it might completely destroy my retrosynthesis. So imagination should be till my starting material, and then from that starting material how can I get back my target molecule. To know about more about these disconnections, we have certain rules which we will be doing in our next discussion. But before we do that, there is a concept called as functional group interconversions. The operation of writing one functional group for another so that the disconnection becomes possible. This we can say that, like for example, for the NH2 group I can write NO2. That means for one functional group I am writing a different functional group so that easily I can do a disconnection. The reverse of a chemical reaction, imaginary breaking of bonds, this is called as disconnection by the conversion of one functional group into another. Now such type of writing one functional group for the another system, they are called as functional group interconversion. Now for example, we can observe that there is a presence of NH2. In place of NH2, I am writing NO2. That means I am writing one functional group to the other. That means if I do a reduction on this NO2 system, I can easily get back my NH2. On the arrow mark, we have written reduction because we are trying to do a backward reaction. Further, when I write a forward reaction, I will write nitro group. Upon reduction, I am going to get an NH2 system. We have written a forward reaction under the arrow. This shows the functional group interconversion is possible and highlights potential problems. That means for one group to the other group, we can write the system and then we can get back my desired functional group easily. Functional group interconversion do not simplify a structure, but they do overcome problems and or allow disconnections that will simply give me the target molecule. So in this way, they do not actually simplify the structure, but if it is difficult for getting one functional group, instead of writing one functional group, I can write another functional group and easily I can try to do a disconnection. So this is what is called as functional group interconversion. Then comes a concept called as reagent. A compound which reacts to give an intermediate in the planned synthesis or to give a target molecule itself. Any compound which is going to give me a reaction to get me my final target molecule can be said to be a reagent. Reagent can also be counted as a synthetic equivalent, where the synthetic equivalent is going to react and then further it is going to give me my target molecule. Yes, the reagent can be said to be a synthetic equivalent of a synthon. What is the synthetic equivalent? A reagent carrying out the function of a synthon which cannot itself be used, often because it is too unstable. We have already seen that synthons are the species which are intermediate species which cannot be commercially available to us. Instead, what we do is we convert the synthons into the respective synthetic equivalents, and further these synthetic equivalents, which are also called as reagent, can be utilized to get the target molecule. Now for example, if this is my target molecule, what we have? We have a cyclopentanone system with a long chain system and an OH. How can I achieve this particular system? My reagent can be cyclopentane system with an MgBr, that is cyclopentane system with a Grignard reagent like MgBr. This can react with a long chain system in the presence of an ether and protonic environment to get me a target. So these are said to be a synthetic equivalents. The second type of synthetic equivalent is cyclopentane system with a carbonyl carbon in the presence of sodium borohydride or lithium borohydride in the presence of solvent and protonic environment. Across the carbonyl carbon there is a reduction to get me my target molecule. The other system through which I can get my target molecule is cyclopentane system containing a carbonyl carbon and a long chain system containing a lithium. In the presence of ether and protonic environment, I can get a long chain system and an attack onto the carbonyl carbon so that I get an OH and H respectively. So these compounds which are said to give me a forward reaction to achieve my target molecule, they can be said to be a reagents or synthetic equivalents respectively. So synthetic equivalents can also be called as reagents system. So in this particular discussion, we have tried to learn about the reagents, we have tried to learn about the functional group interconversions, we have learnt about disconnection as to how the disconnection should not be in a short-sighted way, rather it should be completely far-sighted. And then we have tried to understood if there is a type of acceptor type of synthon system, how can I get its respective synthetic equivalent? If there is a presence of a donor type of synthon system, how can I get its synthetic equivalent? And then how we could get a concerted transformation, heterolytic cleavage, homolytic cleavage, and then how the disconnection of the bond is possible in 3 different ways. And then we have also understood about how the synthons are of 2 types. One is a donor synthon and acceptor synthon. In the next discussion, we will be understanding more about the disconnection. As of now, this has laid a firm system about synthons and synthetic equivalents and how the synthetic equivalent can be renamed as a reagent system. Thank you.